This lesson is an introduction to the concept of pressure in physics. Pressure is defined to be force per unit area. Okay, so we can write that in symbols as P equals F over A, and the units will be the units of force, which is the Newton, over the units of area, which is the square meter. And the Newton per square meter is given its own special name, the Pascal, which is abbreviated as PA. So the best way to explain the idea of pressure is to just show you an example. So let's work this example problem. A nail with a circular point of diameter 0.5 millimeters rests with its point against a board. It's being pushed from the other end with a force of 100 newtons. What pressure is the nail exerting on the board? Okay, so first let's sketch that situation. So we'll draw our board here with the nail. Okay, and it says that we're pushing down with a force of 100 newtons. And the point of the nail down here is a circle with a diameter of 0.5 millimeters. And we're asked to find the pressure that the point of the nail is exerting on the board. So remember, pressure is equal to force per unit area. Now, we already know the force is 100 newtons. So we need to figure out what is the area of the point of the nail that's in contact with the board. So a circle of diameter half a millimeter would be a circle of radius 0.25 millimeters. And we know that the area of a circle is equal to pi r squared. Now we need to have an area in square meters if we want to end up with a pressure in pascals. So we can go ahead and convert this radius into meters from millimeters. So to convert from millimeters to meters, we need to divide by 1,000, right? So let's divide by 1,000. We'll say that 1 meter is 1,000 millimeters. So the millimeters cancel, and we're left with meters. So that's going to give us a radius of 2.5 times 10 to the minus 4 meters. So to find the area of a circle with radius 2.5 times 10 to the minus 4 meters, we'll plug in. So area, we'll use 3.14. That's the approximate value for pi. And then we multiply by 2.5 times 10 to the minus 4 meters squared. And we get an answer of 1.96 times 10 to the minus 7 square meters. So now that we know both the pressure, or now that we know both the force and the area, we can figure out the pressure. Okay, we have that the pressure is 100 newtons divided by 1.96 times 10 to the negative 7 square meters. So you plug that into your calculator. We get 5.1 times 10 to the 8 Pascal. That's newtons per square meter, or Pascal. Now that's a big number. It's a very big number. 5.1 times 10 to the 8, that's about 500 million pascals. So that is a big number, but that's okay because a nail has a very small area. And remember, even though we're only applying a force of 100 newtons, the idea of pressure is that it tells you not just how much force you're applying, but the area over which that force is spread out. So if it's spread out over a really big area, it'll be a low pressure. But if you're spreading a force out over just a tiny area, it will be a huge pressure. In this case, about 500 million Pascal. So at this point, I just want to caution you about a mistake that I commonly see students make. And that is, if you're going to convert area from one unit to another, then you have to multiply by the length conversion factor squared. I'll show you what I mean by that by going back to the example that we just worked. In the example we just worked, the radius of the point of the nail was 0.25 millimeters. And if you were to plug that into the area equation, the area of a circle is equal to pi r squared, then we would get that the area is 0.196 square millimeters. Now, in the example, I went ahead and converted the radius from millimeters to meters. But in some problems, you may be given the area, and the area might be given in a unit other than square meters. For example, what if the example had been that the area of the nail, of the point of the nail, is 0.196 square millimeters? Then we would have to convert from square millimeters to square meters. But it's not exactly the same thing as converting from millimeters to meters. If I want to convert this to square meters, and I put 1 meter is 1,000 millimeters, then this millimeter would only cancel one of those millimeters. And I would have millimeters times meters is my unit. Well, that's not what I want. I need square meters. So what you need to do is you have to square the conversion factor. So now I have, if you say that would be 1 meter squared here, and then 1,000 millimeters squared here, so the square millimeters are now canceled. So instead of dividing by 1,000, I have to divide by 1,000 squared. If I do that, then I will get the right answer. I will get the same area that we got earlier, which was 1.96 times 10 to the minus 7 meters squared. So I do see a lot of beginning students, oops, not millimeters squared, just meters squared. I do see a lot of beginning students forget to square this conversion factor if you're converting area from one thing to another. So make sure you don't do that. Okay, now one more thing before we finish the lesson, and that's a check your understanding question. Okay, so the question is, why do snowshoes help you walk on the snow? And I've given you 3 possible choices there, whether or not they reduce the force, the pressure, or both. I want you to pause the video, think about what your answer is, and when you think you've got the answer, push play, and I will explain what the answer is in the next slide. Okay, are you ready? Then the correct answer is B. Snowshoes reduce the pressure on the snow. If you have if you have regular shoes on, then your footprint might be this big on the snow. If you have snowshoes on, then your footprint might be this big on the snow. So what we're changing is the area of the shoe. Your weight does not change. And because your weight doesn't change, the force that you apply to the snow does not change. However, the snowshoe allows you to spread that same amount of force over a bigger area, which means that you're reducing the pressure on the snow. So even though you still weigh the same that you did, the pressure per unit area, the force per unit area on the snow has gone down, and you're less likely to sink down far into the snow because of that.